So we are talking about the gravitational force and that gravitational force F. This depends on the mass m1 and m2. If two masses m1 and m2 are at the separation of distance drr, so this is inversely proportional to d square. With this gravitational constant capital Z, this is universal gravitational constant. Its value is this Z is actually equal to 6.67 into 10 to the power minus 11, and this is Newton meter square by kg square. And we have calculated in CGS system also. In the last class, we were trying to find that experimental calculation or experimental observation of this gravitational constant G, and it is taken by Cavendish. So if there is a force, then according to Newton, obviously there must be acceleration. So in this class we will talk about that acceleration due to this gravitational force. So acceleration due to this gravitational force is known as, represented by Z, it is known as acceleration due to gravity. So if this is that object at particular height, and this is our earth, and of radius r, and it is falling with it is just dropped from a particular height, then it's this will come to this earth with increasing speed, increasing, I should say, velocity. And since velocity is increasing, there is variation in velocity with the time, means this is accelerating body. So this will be accelerating body. So with varying velocity, its speed increases, and this is accelerating body. So this acceleration, which is because of this gravitational force of Earth. Why this is so? Because this acceleration is because of gravitational force of Earth. That's why this is known as acceleration due to gravity. So one can define this acceleration due to gravity as the acceleration due to gravitational force, acceleration of a body due to gravitational force is known as acceleration due to gravity. So the acceleration of any body which is because of the gravitational force, that gravitational force is attraction force of our earth or that big body, then this is known as acceleration due to gravity. Now we can formulate this acceleration due to gravity with a very simple formula. So here let us say this is at the height h from the surface of earth. So the total, and this is r, the radius of this earth. Then from the center of, this is the center, and let's say here its velocity is v, and it is moving with increasing velocity. So the force on this body A, the force applied by earth on body A is, that will be the gravitational force, and this is Fz, it is equivalent to, so this Fz is equivalent to Z. If the mass of this small body, this is a small m, the mass of our earth is capital M, then this is m capital M by this force, this is, let's say, r plus h square. Since this h is much less than r, then one can write this Fz, it is equivalent to Gmm by r square. Or one can compare this with that Newton formula for force. From Newton formula for force is equivalent to mass multiplied by acceleration. Mass multiplied by acceleration. and this mass of this body is m. Acceleration, here we are taking as acceleration due to gravity, so this is mz. Then we can compare, this is equation 1, this is equation 2. So by comparing equation 1 and 2, we will have, this is mz, it is equal to z mm by r square. This m can be cancelled. This g is equal to capital Z m by r square. One can write also this z r square is equal to z. So this value of this z, this depends on mass of that body, means towards that body is moving, means here this is mass of our earth, and this r is that radius of this radius of that body. So we will take the radius of our earth. So in order to calculate the mass that acceleration due to gravity on the surface of that moon, then we have to take mass of moon and the radius of moon. Okay, so this is acceleration due to gravity of our earth. Then we have to take this mass and this radius, and this z calculated for our earth is 9.81, and the unit will be meter per second square, or 981 centimeter second square. So in SI system or MK system, this is 9.81. For mathematical calculation, many times we take this, generally take it, this is equivalent to 10, but this exact value is 9.81 meter per second square, and in CGS system, it's a 981 centimeter per second square. So this capital G is gravitational constant. This is a universal constant. This G depends on mass. Mass is much more. Then obviously acceleration due to gravity, that will be more. And this also depends on this R. It is inversely proportional to R square. So if the radius of that body is smaller, then acceleration due to gravity, that will be more. Now, so apart from this z actually depends on height and depth of that material. So variation of z, let us have variation of z. So this is on the surface of earth, remember this. This z is on the surface of earth. So first of all, let us calculate the first acceleration z at height h. This is that our earth. This is the radius of earth r. Mass is capital M, and this is that body at a particular height h from the surface of earth, and here at this point, in this point, as acceleration due to gravity is g. So we have to calculate this acceleration due to gravity, that is z prime at height h. We have to calculate this z prime. So first, what we are considering, mass of earth. This is capital M. Second, radius of our earth. This is calculated as capital. This is taken as r. And the third, acceleration due to gravity on the surface of earth. Means let us have this point here. This point is A, and this point is B. So earth at point A is z, and what we have to calculate, acceleration due to gravity at height h from the surface of earth, that is at point B. we have to calculate this G prime. We have to find this. So first we know this that acceleration due to gravity at point A here, if this body is somewhere here, so at A, this we will compare this mass multiplied by Z, that is equal to just recently calculated. Here the mass of that body is M, so the force exerted by that earth is mc toward the center, and this is equivalent to Gm by r square, or to C it is equivalent to Gm by r square. Just we have calculated this equation, so this is equation the first. Okay. Now let us calculate that acceleration due to gravity at point B. Now at B, that here the mass we will take is equivalent to m, and the acceleration due to gravity, let's say this is mg prime. Here this is mg, in this point this is mg prime, and this is equal to gmm by, in place of r we will take r plus, this is r and this is h, so we will take this is r plus h square. Okay, so let us further use some more mathematics. So this m, this can be cancelled, and this implies g prime is equal to gm. Now let us do some more mathematics. Let us take this r square common from this bracket, and one can write 1 plus h upon r square. Can we write like this? Just taking this r out of this bracket, so this r is here, so here there will be 1, and here this is h only, so this will be in denominator. So when we multiply this r square, then this will be r square. When multiplied this r square, then this is in terms of the square, so this is r plus h, so this is r plus h. So we can write like this, and also we can have this gm by r square. And why we are doing this? Because this gm by r square is actually g. We have to replace this gm by r square by z, and 1 plus h upon r square, now with minus 2 power. So this is 1 plus h square. Numerator may that will be with minus 2. R. This is h upon r minus 2. Okay. Now I will use binomial theorem. Since h is much less than r, then by using binomial theorem, this g prime, it is equivalent to, this is z, and 1 minus 2h by r. This power, it is multiplied inside by using this binomial theorem. So in mathematics you should remember this. If since 1 plus x to the power n, it is equivalent to 1 plus nx, if x is much less than 1. If this is much less than 1, then this power, it is multiplied inside. So here this is the case. Since h is much less than r, this r is a bigger quantity. So this quantity with comparable to a1, this will be very small quantity. So r, you can write h upon r is much less than 1. Then by using this binomial theorem, this minus 2 can be multiplied here. So this is z prime, it is equivalent to z 1 minus 2h by r. Here one thing you should remember, that this particular equation, this particular formula is only applicable when this h is much less than r. If you are using this h is equivalent to r, then this formula cannot be used. Then directly you have to use this the first one. You have to calculate g prime is equal to pqm by r plus h. So you have to multiply directly and divide that. This is the good approximation, and this approximation is only applicable when we take this value h is much less than r. So when that object is at the near about our earth, then this equation can be used. Okay, so this is now we are keeping this object inside the earth at depth d or at the depth h inside the earth, the variation of this z. So g at second at the depth of h. So this is our earth. This is center, and we are just digging here, and at the depth of h, this h, here that body is somewhere here. Here this is that body of mass m. Radius is r. Capital M is the mass of our earth. Okay, so now this is the second case where we have to calculate that acceleration due to gravity inside the earth at the depth of h. So here, obviously at the surface we will take this is equivalent to z, and here we have to consider that is z prime. So this is the point A, and this is point B. So at point A, the acceleration due to gravity, z is same, that is zm by r square. This is equation number first. So the first equation is as it is. Now this z depends on mass and the r square, we know very well. So here when we want to calculate this z prime, then this z prime actually depends on the mass of this part of earth. Because at that surface, the effect of complete earth is there. At the surface, at point A, the effect of complete earth is there. And we calculate this is mz, that is equivalent to gm by r square. But inside the depth of h, the effect of this part will be calculated. So first of all, we have to calculate the mass of this part. Let's say this is h and this is r, then this depth, this will be r minus h. Okay, so complete is r, this is h, so this part is r minus h. So first of all, we have to calculate this m prime. This is the mass of this inner part of this earth, and we have to calculate first. And in order to calculate this, we have to calculate the density of this earth, and let us try to calculate it. So by assuming the mass of earth is uniformly distributed, the density of earth is, let's say that is rho, it is equal to, density will be mass upon volume. So this is mass, this is mass is m, and volume is 4 pi by 3 r cube. By assuming this is a very big sphere, so the m is mass and this is volume. So volume is 4 pi by 3 r cube. This is the density. So the effective mass of Earth. Effective mass means that mass which is in effect to calculate this G prime. That's effective mass of Earth. That is M prime. It is equal to, now the density, rho multiplied by volume of inner part. And that M prime is equal to, rho is this is M upon 4 pi by 3 R cube multiplied by that volume is 4 pi by 3, and in spite of this R cube we will take this R minus H cube, because that radius of that small part is R minus H. So this can be cancelled. R M prime, this is equal to M R minus H by R minus H cube by R cube. So now we will use the similar one. So here at point B, this is point B. So therefore at point B we can take this mass is that small m is small m, the body of mass, and that acceleration due to gravity, that is Z prime. And the second part, that is the gravitational force, so we will use the same gravitational constant. The mass of that object is small m, but we will take this M prime. M prime is that effective mass of this Earth. We are not considering the complete mass of Earth, we are just considering taking this effective mass of Earth, and we have calculated that effective mass. Okay, why we are doing so? Because that body is inside. So this outer part, this cannot, there will be no effect of this outer part of that body in the this object. Only this part will affect this one. So this will attract toward the center. So this is Gm, capital M is the mass of this part, by this radius is R minus H square. The distance is R minus H. So this will be M can cancel here, and I will put this M prime from this. So this is Z prime, it is equal to G M prime is, this is M R minus H cube by R cube upon R minus H square. So this is Z prime, it is equal to this square, it can be cancelled, and this is Zm by R square multiplied by R minus H by R. Check it. Okay, this R minus H square can be cancelled. Here that R minus H will remain, and here this R cube, this can be divided into two parts, R square multiplied by R, and this Gm by R square can be substituted as Z prime, it is equivalent to Z 1 minus H upon R. Okay, so we had at height h, we are checking that G prime is equivalent to G 1 minus 2H by R, and there is one approximation. That approximation is H must be much less than the value of R, but here there is no such a condition. G prime is equivalent to G 1 minus H by R. If we take H is equivalent to R, means at the center of Earth here, H is equivalent to R, that's complete H is equivalent to R. So this G prime, that G prime is equivalent to G 1 minus 1, and that is equivalent to 0. So at the center of Earth, the acceleration due to gravity is 0 according to this. Okay, so just rederive these two formula because these two are important. And in the next class we will discuss about the variation of that acceleration due to gravity z due to the rotation of our Earth. It also affects rotation of our Earth, also affects the acceleration due to gravity. So okay, thank you.